Hello, everyone. My name is Oliver Franzke, and I'm a principal software engineer at Double Fine Productions. And today I want to talk about parallel computing in video games. Now, I've been working in games for nearly a quarter of a century, and during that time, I was fortunate enough to work for companies like Sony and LucasArts, and now for Double Fine for quite some time. So here you can see some of the games I worked on over the years. And my specialty is to work on graphics, so bridging the gap between the art department um, and engineering, so like translating the vision of the art department into math and then into code. Um, but I also work on low-level game technology, which in like game development terms is often called the game engine. So this piece of software that runs between the hardware and the actual creative team, like the game designers and the gameplay programmers. Um, but of course, we're not here to talk about me, we're here to talk about video games. And before we're going to look at specifically how parallelism has become more important to making video games over the years, we kind of first have to figure out what video games actually are. And on a conceptual level, a video game can be represented as the so-called game loop. And so that is literally a loop that keeps spinning while the game is running. And in that, we're first creating the player input, which could be kind of the states of the buttons on a game controller or mouse and keyboard, could be a touchscreen or a gyro or something like that. And with that player input, we're then updating the state of the game, which is also sometimes called the simulation step. And then finally, we're representing the game state in some form. Now, obviously, visually, so graphics, but also via sound or haptics, like controller rumble and things like that. Now, the inner part of this loop is called a frame. And in video games, kind of the slowest frame rate that's acceptable these days is 30 frames per second. And when you run at 30 frames per second, that means you have only around 33.3 milliseconds to compute this inner part of the loop. And moreover, a lot of games these days definitely strive to run at 60 hertz, in which case you only have around 16.6 milliseconds to compute this inner part of the loop. Now that we kind of have a conceptual idea what a game is, I want to first take a quick look historically how concurrent execution and parallel hardware has become more prominent over the years. And then we're going to look very specifically at how we're parallelizing graphics these days. And then in contrast to that, we're going to look at the challenges of parallelizing gameplay logic. And finally, we're going to look at an alternative architecture that kind of tries to get around these challenges of parallelizing gameplay. Now, the very first game console that I ever had access to was the Nintendo Game Boy, which was released in 1989 by Nintendo. And for me, I was able to get my hands on that in the early 90s since I grew up in East Germany. And so I had to wait for the Berlin Wall to fall to actually be able to play games on the Game Boy. And if you compare the speed of the Nintendo Game Boy, of the hardware, with the speed of the latest flagship console from Microsoft, the Xbox Series X, which you can see here, you can kind of do some hand-wavy math and figure out that the Xbox is about 12 million times faster than the Game Boy. And of course, whenever you do these kind of quantitative comparisons, it's only logical that you want to also then ask the question, well, does that mean that a game like Forza Horizon by Playground Games is 12 million times more fun than Tetris? And of course, that's easy to figure out. All you need to do is compute this integral. No, I'm joking. Of course, there's no way to compute fun, but it is certainly true that games have become more complex and sophisticated over the years, and partially that's due to the availability of parallel computing hardware. And whether or not this sophistication translates to fun is, of course, up to the player. But let's look at this kind of in terms of kind of a historic evolution. Now, we're going to start just like before with the Game Boy and use this as kind of our reference piece of hardware. And then so we can look at Nintendo Entertainment System, released in 1990. The PlayStation 1, released in 1994, which marked kind of the era of transition from 2D to 3D graphics. The PlayStation 2, released in 2000, was obviously one of the most successful game consoles of all time. One of my favorite game consoles was the Xbox 360, because as a game developer, it was just so easy to work with that machine and had a lot of fun games on there. And then as a representative for the current generation of consoles, we're going to use the PlayStation 5 here, released in 2020. Now, if you do the same kind of hand-wavy math that I've done just a second ago, you can kind of see that over time, the performance increase, which is kind of denoted at the bottom here as the speed up factors, has increased exponentially. So for example, the Super Nintendo Entertainment System is about twice as fast as the Game Boy, the PlayStation 1 is around 32 times faster than the Game Boy, and so on, and the PlayStation 5 around 10 million times faster. So we had this exponential increase. And to some degree, we need this, right, to make games that are more complex and sophisticated, like I mentioned. But to some degree, this increase of performance also was driven by other external factors. For example, if you look at the output resolutions over time, you can see a very obvious trend. Now you have the representation for the resolution of the Game Boy down here at the bottom left. The Game Boy had an output of around 160 by 144 pixels. Then the Super Nintendo Entertainment System was not a handheld device, so you had to plug it into a CRT TV, had a higher resolution, and then on until these days on Xbox Series X and PlayStation 5, games commonly render at 4K resolutions, which means 3840 by 2160 pixels. So just visually you can see that there is an exponentially larger number of pixels to deal with over time. And so of course we need the hardware to just deal with this increase of memory bandwidth that we have to work with. And this also becomes obvious when you look at the buffer that's required to store the image that's been displayed to the user, which is called the frame buffer. So for example, for the Game Boy, where I said we had 160 by 144 pixels, each pixel could have 4 shades of green, which means we need 2 bits, so that the frame buffer size is 5.6 kilobytes. And if you compare this to the current generation of consoles, where we have the 4K resolution with 32 bits per pixel, it means we need a frame buffer that's roughly 32 megabytes. And I do want to point out that this scale here on the left, that denotes kind of the scale for the frame buffer size, is log-based. So even though this looks kind of like a linear increase, it is in fact exponential increase. And so it won't come as a surprise that the amount of hardware that's dedicated to working with graphics has also increased exponentially over the years. So the curve, this pink curve here that's overlaid, is the kind of dedicated hardware in a game console that specifically is designed to work on graphics tasks. So for example, the Super Nintendo Entertainment System had like a coprocessor that worked on graphics that could do stuff alongside the main CPU. The PlayStation 2 had these 16 pixel units, which essentially represents like a fixed function pipeline implementation for 3D graphics. The Xbox 360 had a programmable GPU. And now the current generation of consoles have a fairly standard GPU. And for example, the PlayStation 5 has a GPU which has 2,304 shader cores to work with. So again, both scales on the left and right side are log-based. So what we're looking at here is definitely an exponential increase. And we can see something similar on the side of the CPU. So the bars here denote the clock speed. And you can see that the clock speed size has increased exponentially for some amount of time, right about like the era of the 360, and then it kind of leveled out. And that tracks with Moore's law, right, where we doubled clock speed every 18 months or so until we had squeezed in all transistors onto the chip that we can possibly fit on there. And then the path forward, like in this era here, when kind of the amount of speed up per clock, per CPU has kind of leveled out, the way forward to gain performance was to add parallelism. So the Xbox 360, for example, had 3 CPU cores and 6 hardware threads, and the PS5 has 8 cores and 16 hardware threads. So you can see also here we have this kind of exponential graph. And I do want to very briefly point out, some of you may have noticed that the clock speed for the SNES is actually slightly smaller than the Game Boy. And that's true, just if you look at the raw megahertz, the SNES chip was slightly slower, but its bus size was wider. So we went from 8-bit to 16-bit, and therefore it could push through much more data, even though the actual clock speed was slower. So that's why the SNES is faster, just because they increased the amount of data that you could process per clock cycle, essentially. Anyway, so you can see that both on the CPU side as well as on the GPU side, we had these exponential increases over time. And while some of it we need to, for example, deal with this kind of exponentially larger number of pixels for the output resolution, we still have a lot of processing power left over. So let's figure out how we can apply this to our game loop and parallelize parts of it. And let's start with the representation of the game state. And specifically, we're going to look at graphics. So let's zoom in on the GPU of a PlayStation 5 as a representative for the current generation of consoles. And what we see is kind of this conceptual model. The PlayStation 5 GPU has 36 compute units, which each one of those has 64 shader cores, which means that in total, the GPU has 2,304 shader cores, which each tick at a speed of around 2.23 gigahertz. So this is a mind-boggling amount of compute that we have available and that we can work with. But of course, this comes with some constraints, because all of the shader cores within a compute unit have to share memory, so they can't just allocate memory freely, and so that kind of defines also how many shader cores can actually do useful work, because only if you can allocate memory for a shader core to do stuff, you can use it. And also, they all execute code in lockstep. So all of these shader cores run the same piece of program, which in GPU lingo is called a shader program. So each one of these cores are essentially going to execute the same line of code, but you get a lot of speed up because you're doing this on potentially on 64 cores at the same time. So for the time investment of one operation, you can actually get 64 things done in theory. And that's good, because there's a lot of work that needs to be done. Now, so what is the kind of work that you can do on a GPU? Well, these days, it's actually has become very important to just do general purpose computational work. And what I mean by that is that we're going to have a set of buffers that we want to do some math on. And so we're going to run a so-called compute shader on that takes the inputs from these buffers, transforms them in some way, and then writes out the resulting buffers. And in games, often we use this for kind of 2D image processing, for example, anti-aliasing, so like the smoothing of the output image. Other aspects would be kind of evaluating like a camera model, so depth of field, which parts of an image should be in focus and which parts should be blurred, Or global illumination is another example, so how light reflects in the scene. These are all like common examples that you can use a compute shader for. But of course, historically, the compute shader came later, and what the GPU was really designed for was to work with 3D graphics. And I want to very briefly kind of give an introduction of how the 3D graphics works here, in case you never heard this. So the idea is that if you have some kind of object in a 3D world, like a cube, for example, you're gonna represent it through a so-called triangle mesh. And for the triangle mesh, you have these corner points, which are called vertices, and they are connected with edges to form triangles. And so if you want to draw this on a graphics card, the first step you have to do is to take each one of these points that are defined in 3D space and project them onto the camera plane. And this is done through a so-called vertex shader, which we write as game developers. And so here, typically what we do is we take a 4x4 component matrix, which contains the projection of a 3D point onto the 2D camera plane. So we're going to do this projection, and there's some other math you can do here. Then once we have these kind of triangles defined and computed, then we need to figure out what are going to be kind of the potential pixels that are inside of this triangle. So, the input here is these green points and the connecting lines. So now we need to figure out which are the pixels in the actual output image that are inside of the triangle. And this is called the so-called rasterization step. And then using these fragments, pixel fragments, we can finally compute the final color for these pixels, which is called pixel shading. So if you imagine, drawing a rock in a game will look very different than a shiny piece of metal, depending on how the light shines on it, for example. So this is done by a piece of program called the pixel shader that we write as game developers, in which we evaluate lighting and surface models, which have become quite complex these days in the era of physically based rendering. And so, this pixel shader will be executed on all of these pixel fragments, and then essentially they will end up with some very specific color. Now, the thing is that the reason why the GPU was so successful as a piece of hardware and has gained this prominence is because this graphics pipeline is what's often called embarrassingly parallel. And what we mean by that is that we can execute a lot of things at the same time. So for example, when we want to kind of project these 3D points for the model onto the camera plane, we can do this on all those vertices at the same time, because it really doesn't matter in which order these are transformed. Like, you're just going to apply like a matrix multiplication essentially to each one of these 3D locations. And so you can take these 8 vertices and compute the projection at the same time. And so this maps perfectly onto our GPU model there, where we have these shader cores that all execute the same code. And so it can just do this transformation on these 8 vertices at the same time for the cost of essentially 1. And the same is true for rasterization, although this is a fixed function pipeline still these days. So in other words, it's not programmed by the game developer. And also for the pixel shading. So there's no dependency between pixels, and the color of one pixel over here doesn't really depend on the pixel color over there. So we can compute the color for all of these pixels at the same time as kind of independent operation, which again maps perfectly to this model of the GPU, not surprisingly, of course, where we can run the same kind of code on multiple pixels, for example. And that's good news, right? So we can do a lot of work here and crunch numbers very quickly, because video games actually are very complex visually these days. So here's a screenshot of the game Keeper, which I worked on most recently, which was released in October of 2025. And in this game, you play as this walking lighthouse with legs, which has a bird body, and you explore this kind of post-apocalyptic kind of mysterious world. And if we for 1 second just look at one element of the scene, like this piece of rock here, we can isolate it and see that, it looks like that. And then if we look at just the amount of triangles that this model is made of, we can see there's actually quite a lot of triangles that are used here. So each one of these like pink lines is an edge between vertices, and so you can barely actually see the underlying geometry because the vertex density is so high. And this is especially surprising if you look at kind of how models used to be represented in the previous generation of consoles, so the time of the PlayStation 4 and the Xbox One era. You can see there's way fewer vertices that we worked with. And this is due partially to the fact that these days we just have, faster GPUs to work with, but also there's been quite a few algorithmic advancements, so we can work with just higher density models. And that's good news for the art department because we can just fill the world with kind of very dense, beautiful models much quicker. And we don't need to think too much about how we're gonna reduce their geometric complexity, which was a big part of the pipeline in the past. But of course, this rock is just one element in this frame, right? There's a lot of other things going on. We have the ground with the lighthouse itself, of course. We have kind of the little grass elements and other weird plants, these kind of strange trees back there. We have clouds. And for Keeper, we chose to make the game with this kind of painterly art style, which means we have these brushstrokes to work with, for example. So all of these objects need to be processed and drawn. And let's take a look at what that actually looks like under the, let's take a peek under the hood of the GPU. So here I took a GPU trace using a tool called Pix of this frame in Keeper that we just saw. And the details here don't matter, but there's a couple of things I want to point out, and we're going to look at several elements in this scene in the following slides. So first of all, I want you to notice that we have these kind of two kind of lanes up here. These are called pipes. So at the top, we have the graphics pipeline. So this is what I mentioned earlier, where we work with vertices and pixels and rasterization. And then here we have the compute pipeline, which is doing this kind of general purpose compute work. And so there's a lot of boxes here horizontally, and these are all different steps that go into making a frame. And ultimately, these blue boxes are the final pieces of work that the GPU is doing. And these other ones are just kind of a high-level representation of the work, so they're kind of clustered together. And so you can see, we have graphics work and compute work that kind of laid out like these parallel tracks. But of course, for the GPU, it doesn't differentiate between those. It will work on graphics and compute work in the same way, like it doesn't really schedule this separately. But it's for us as developers, it's much nicer to have it like this because it makes it easier to debug if something's going wrong and also to reason about performance implications. And under these two pipes, you can see this part of the trace, which is called the wave occupancy graph. And what this essentially tells us is how much of the computational resources that the GPU has to offer we're using. And ideally, we would like to have this part down here filled with colors. Doesn't matter which colors, but ideally we wouldn't want to see so much white. And so you can see there's a lot of like this light gray, white here, and that means the GPU is idling a lot, or a lot of shader cores are idling. They're not doing useful work. So there would be some more optimization work required here to make this faster. But for Keeper, we had a very small, low-level programming team, so we didn't have time to squeeze out every little clock cycle on the GPU. But let's look at some parts of this GPU trace. So first off, I would like to highlight this area right here in the beginning. And what you can see down here in the wave occupancy graph is that we have this big chunk of blue, and underneath this we have this kind of narrow part of darker green. And if we look at the legend on the right side here, we can see what type of work this is, and specifically this is work in the graphics pipeline. So for example, the kind of green at the bottom, refers to vertex shading. And so you can see the GPU starts working on this model to draw this model, whatever it may be. So it's going to start like rising up, and it's going to start projecting vertices that this model is made of, and kind of storing the triangles in a bit of intermediate memory. And then at some point it has processed enough vertices so that the pixel shader can start its work and draw or fill in the colors for the pixels inside of those triangles. So at this point you can see the pixel shader very quickly rises up and fills the GPU with work that's pixel shading. So this is that part here. And I do want to point out that this overlap of work is done entirely by the GPU. As game developers, we don't really have any input on this. But it does make a lot of sense to do it like this. And of course, the other way would be, you could imagine like the GPU would process all the vertices first. So you would have one big chunk of green in the beginning, and then one big chunk of blue after that. But this would mean you would need a lot of intermediate memory, right, to store all these transformed vertices before the pixel shader can start work. And instead, what we're doing, we're essentially creating like a stable pipeline where we have a little bit of intermediate memory, and the vertex shader is writing these processed triangles into this intermediate memory, and then the pixel shader reads out the triangles that are done and processes those. So it's kind of a very fast pipeline, and the graphics card does it like this to optimize throughput, so to just get more work done in a piece of time. Let's look at a different part of the frame over here. So we can see we have different colors that we see. So at the bottom here we have this yellow block, and that refers to general purpose compute, so running a compute shader. And so you can see it's doing some work, then it kind of increases, it's doing some more work, and then it tapers off. I do want to point out that it might be perhaps a little bit weird that it's not filling the whole chunk right here in the wave occupancy graph. So only some amount of the shader cores on the GPU are actually running this compute shader. And that's probably because the shader requires a lot of kind of intermediate memory, so like registers and intermediate variables it's writing stuff into and reading stuff from. And because of that, it requires quite a lot of temporary memory. And so when it allocates the memory for these shader cores on a compute unit, it can only allocate a couple of compute units, like maybe 3 or 4, even though there's 64 available, right? Since there's only memory to run 4 of the cores, the rest of them will just sit idling. And this is probably what we're seeing here. And so if you wanted to change this and make this more optimal, you would need to make the shader simpler, removing some of this intermediate variables, and also maybe just removing some ALU operations, for example. But what you can see is there's another color layered on top with this kind of light green, which refers to asynchronous compute work. So the idea here is that up until now, when we talked about the pixel shading, vertex shading, and now the compute shader, this is the kind of work we actually schedule essentially as game developers. So we say, draw this object first, and then draw that object, and then take the output of this draw operation and do some other work with that, and the same for this compute shader. But sometimes you have some operation where you have the kind of inputs ready at an early part in the frame, and you just need the results at some later part in the frame, but you don't exactly care when in the frame this is computed. And so we can tell the GPU, like, here's some work, it doesn't really matter when you do it, just do it at some point whenever it makes sense. And then the GPU work scheduler will essentially figure out when we have GPU cores available that can allocate to work on this operation, and then it will just overlay kind of this work asynchronously on top of other work. And this is done to increase the throughput here. So we're just hiding some of the latency of some of these operations by running things in parallel. And this also works with graphics work. I just want to point that out here. So asynchronous compute, which is this light green up here, can overlay on top of pixel and vertex shading, just in the same way it does with compute shading. So you can see, like, even on the GPU, we have a fair amount of kind of parallelism, even within, GPU execution. And whenever that's the case, we have to deal with some amount of synchronization. So for example, here we have an example where the compute shader wants to do some transformation on a buffer, but it realizes that when it wants to start this execution, that it doesn't have all the inputs ready yet for that. And then so here picks us nice and actually shows us when this input will be started to be produced, which is up here in the graphics pipeline. So the compute shader, hits this intersection, says, okay, I have to wait, and then, it waits and can't do anything else in the meantime. But the graphics pipeline is still working and drawing some models. So you can see down here, there's a vertex and pixel shading happening. And at some point, it's done with that, and it's going to start working on the buffer that this compute shader needs. And so that's right here, and then it will start working on drawing this buffer, and eventually it's going to be done, and it's going to signal that to the compute shader that this buffer is ready. And with that, it will unblock this compute pipe, which you can see here, and then there's a flurry of activity on the GPU, on the compute pipeline. So it's going to take the input buffer and finally do all these operations that it was supposed to do. And you can see that actually the graphics pipeline is waiting then on the output of this work that the compute shader was doing. So it itself waited and blocked because it needed the buffer that was produced by the activity that is done by the compute shader. And then so that is, unblocking then the graphics pipeline. And so these orange bars are essentially bubbles in the pipeline where we have to wait for some data, and that's not ideal. Ideally, we would like to avoid this. Now, as you can see, the GPU doesn't completely stall, right? And that's because graphics and compute work is scheduled the same way to execute on the shader cores. So it's not that there's nothing happening there, but still, if we have a more efficient pipeline between graphics and compute lanes, then we could perhaps just increase the throughput on the GPU. And in case you're wondering what kind of buffer this is that we're waiting for here, it's the depth buffer. And so this is essentially an image that tells us how far away each pixel is from the camera, or like the closest surface in that pixel from the camera. So that's what I was waiting on here. Now, if you were looking closely, you may have noticed that up in the top right corner, Pix tells us how long it takes to run all the operations required to draw this frame. And we'll see that this takes around 30 milliseconds. Now, this is interesting, right? Because in the beginning, I mentioned that the kind of slowest frame rate for games is 30 Hertz, which means we only have around 33.3 milliseconds per frame. So that would mean that we only have, around 3 milliseconds to do the rest of computations. But that is a fraud analysis because the GPU is a whole separate piece of hardware that runs in parallel to the CPU. So our game loop really kind of looks like this now, where we remove the drawing step out of the loop because this is done in parallel by the GPU. So we have now these two processes running essentially at the same time. Updating of the game state is still done on the CPU, but the actual drawing is done on the GPU. Now, even though we removed the drawing from the game loop, we still need to tell the GPU what the work is that it's supposed to do. Like, it can't magically know which objects to draw and where they are and what their color is supposed to be. And so we still have to run some code on the CPU, and that's called the render setup. So we essentially assemble all the information required for the GPU to draw the frame. And that on its own is actually quite a complex step. So we're going to break it down into sub-steps, and let's look at this. So On the left side here, we can see kind of the entire game state. So these are like all the objects in the game that you need, like the main character, buildings, the ground, whatever it may be. But we have other things here too, like game logic, for example, that needs to be executed is stored. For example, we may have the state associated with a TCP pipeline for a multiplayer game, or some achievement progress, like all the elements that make a game. And in order to draw this, of course, we're only really interested in the visual parts of the whole game state. And that's called the render scene. So we're going to distill all the visual elements out of the game state, called it the render scene. And that is actually still very complex these days in games. So, it's very common to have thousands to tens of thousands of objects in the render scene. And you can't just send all of those to the graphics card, because the graphics card would then spend cycles on computing stuff that wouldn't be visible, like stuff that's behind the camera, for example. So instead, we want to pare down kind of the amount of objects that we're going to send to the graphics card through so-called culling steps. And we're going to look at this in a little bit more detail in a second. But the point is here we then have a reduced scene that only contains the potentially visible objects. And then we might have some other like dynamic buffers, like particles or other stuff like this that really we don't need to represent in the game state. And then those two things together make up the current render state, which will then assemble into so-called command buffers, which will then send to the GPU that will then render this command buffer into the frame that we can see on screen. So let's look at this culling step here, or specifically there are actually two culling steps I want to talk about. And the first one is the so-called frustum culling. And the idea here is that we're really only interested in the objects that are in the volume that's defined by the camera. So if you imagine a 3D camera, there's almost like this kind of pyramid shape that's coming out that defines the volume of space where the camera can see objects. And so if there's stuff behind the camera or kind of outside of the view frustum, which is what this volume is called, then we can ignore this. And so in order to compute this kind of visibility state, we have to run a little bit of math to figure out whether objects are inside or overlapping with this volume. Now, thankfully, this is an operation where that can be done kind of simultaneously on all the objects. And so we can run this in a thread pool using a parallel for each loop, for example. So we're going to take these thousands to tens of thousands of objects. We're going to just throw them onto worker threads to compute this visibility state that you can see here at the bottom. And once that's done, we can resynchronize. And so essentially here we're hiding the latency of processing all of these objects by doing them all in parallel. And so overall, it requires less time this way. So once we've done that, we want to actually go one step further, and we want to also exclude the objects that are entirely behind other objects and therefore don't contribute to the visible pixels. And this is called occlusion culling. And for that, we actually need the help of the graphics card. And what we're going to do, instead of drawing the full scene with all of kind of its geometric complexity and the colors and textures and shadows and whatnot, we send a simplified version of the scene to the graphics card. And often what we use are these kind of bounding volumes, like these cubes. We're going to send this representation down here at the bottom right to the graphics card, and the graphics card has some mechanism where it can count the number of pixels that were drawn per primitive, and with that we can tell whether or not a primitive is visible, right? If there are no pixels that have been drawn for primitive, then this isn't really visible. But this means, now that we involve the graphics card, that we're gonna have like an asynchronous operation at play here. So at some frame, we're gonna take the objects and like send these simplified proxy volumes to the graphics card. The graphics card is going to start work once all the command buffers have been assembled. And then after that's all done, it can give us back the results. So that means that the next frame, we can actually then use these visibility or occlusion results. So that means we have an asynchronous operation here that spans two different types of hardware that we can use. And of course, that means that our occlusion information will be off by one frame, but often that's not a big deal because objects don't really move that fast. So you can still make use of that. And even if you had problems with objects disappearing when they shouldn't, what you often can do, you can kind of make these boxes bigger and then therefore kind of tweak a little bit the occlusion culling this way. But the point here is we have another form of parallelism at play, one that spans two different types of hardware. Okay, so now that we have this current render state ready, we can go ahead and turn this into the command buffers that the GPU can execute. And these days, we actually use the ability of modern graphics APIs like DirectX and Vulkan to do this also in parallel. And the way we do this is by assembling a frame into a so-called render graph. So the idea is here we're taking, for example, the final output, the final image, and we're decomposing it into independent steps. So we need to compute like some translucency, lighting, shadows, and for example, the depth buffer that we saw earlier. And we're putting them into a graph. So we have the dependencies and therefore the order of these operations kind of well defined, and also kind of how data flows between those. And now that we have this kind of nicely encapsulated, we can in theory compute the parts of the command buffer associated with these steps in parallel on different worker threads. And so some engines are better at this than others, but in theory, this can be done. So you can take all these blue boxes, compute the commands associated with them at the same time, and then essentially copy them all into one big command buffer that the GPU can execute. So here, again, another form of parallelism that is at play. But even though we've done a lot of kind of work here, parallelizing work like the frustum culling and the assembly of the command buffer, the render setup step still actually takes a lot of time, and often that is actually the bottleneck in modern games. So in Unreal Engine, which is what we're using, you can enable this overlay that shows you kind of how long different parts or different processes to make a frame take. So we already saw, for example, the GPU duration, or the time required on the GPU to draw the image takes around like 30 milliseconds. But we can see here that render setup, which by Unreal is called draw, also takes around 33 milliseconds. So again, essentially the time associated with a whole frame. And this time we don't have another piece of dedicated hardware for this render setup step that we just magically will gain parallelism from. So we need to do this ourselves and put this work onto a thread. So the idea here is essentially that we're also taking the render setup step out of the game frame, out of the game loop, and running that on a separate thread. So now we essentially have this game loop, right? Before we start the loop, we're gonna launch the render thread, which will then spin on its own. And then in the actual core game loop, all we now need to do is like get the play input, update the game state. And then so we have these three processes that run in parallel, updating the game state, executing the render setup, so getting the data ready for the GPU to draw the image, and then the GPU on its own is actually drawing or executing these command buffers and therefore drawing the frame. But of course, this has an implication. We still need to update the render scene depending on what happens in the frame. So for example, if we update the position of the main player, right, you press the stick on a controller and the main player has moved in this update function here, we need to tell the render thread that this object has moved. It doesn't just magically, it's not magically aware of that. And now that we have these separate threads, essentially, so these are two different CPU threads, update and render thread up, we need to do this using, for example, a producer-consumer pattern, which is what Unreal uses to send this information from the main thread, the game thread, to the render thread. So you can see here, for example, we're adding a light source, and this is done by queuing up a command for the render thread using this lambda expression. And this part here inside of these braces will be executed on the render thread. And then if we change the color, for example, you can see we're also doing something similar, only that we're now updating the color and brightness on the render thread. So this is essentially like queued up on the game thread, and it's going to be put into some kind of queue. And then when the render thread starts its frame, it will first pull all of these update commands out of the buffer, execute them, and then it has the current render scene, and then it can do the culling step, and then record the command buffers for that frame. And essentially what that means is that we have a situation like this. When we start the game thread will start its computation and compute the state for the first frame of the game. Then once that is done, the game thread can move on using the player input and compute the state of the game at frame 2. Now, also the render thread can start to get the data ready for the GPU that's based on the frame on frame 1. And then in the next step, finally, the graphics card can start to draw the data associated with the first frame, because it had to bubble through from the game thread to the render thread, eventually to the GPU. And so you can see we have this kind of 3-frame delay of the data. And this has real life implications, because if you think about it, we're reading the player input here at the beginning of frame 1, right? But the player really only sees the results of button presses, for example, at the end of frame 3, when the GPU finally displays the image associated with that player input. So we need to make sure that all of these processes, all of these elements here, stick to the constraints of how long this is allowed to take, because otherwise, like, the time differential between reading the player input and when it's finally seen will increase, and the game will feel sluggish or stutter or something like that, and people are very sensitive to this. All right, let's take a breather. And I think we can say that we were fairly successful at parallelizing the graphics work. So we've done this on multiple levels. We're using the GPU, and then there we're dealing with like parallelism in there. And then even on the CPU, kind of getting the data ready for the GPU, we're utilizing a lot of various forms of parallelism there as well. So let's look at the gameplay logic and how hard can it be to parallelize that? We were successful so far. And it's actually quite a big challenge. So here you can see a screenshot from the game Psychonauts 2 that we at Double Fine released a couple of years ago. And in this game, you play as Raz, which is this character down here in the middle, and you kind of traverse the world by jumping and dashing, running, whatever. And you have to talk to some characters and jump around and fight with some enemies in order to make it to the end of the game. And I want to use this screenshot to illustrate the kind of amount of heterogeneous operations that need to be executed in order to evaluate the game logic and therefore advance the game state. So for example, for the main character, for Raz, we have to first figure out what the movement state is based on the player input. Has the player, pressed the stick on the game controller? So are we supposed to walk or run? Or has the player pressed the button to start a jump, for example? And then if we are walking or running, are we still on the ground? Or are we walking up and down like stairs? Are we colliding with something like a chair or a table that we shouldn't do? And so we're kind of figuring out essentially with that where Raz will be. And once that is done, we can then figure out it's his pose, the so-called animation state. So if we're running, we need to move the legs, for example. But in Psychonauts 2, we had another like parallel system here, in which RAS will, for example, automatically look of objects of interest in the world, which is there to aid the player, while you're playing. But that too has to be computed. Like there are several objects maybe in the world, and it needs to figure out which are the ones that you could potentially look at, and if they're multiple, how do you prioritize those? And then are they even in front of RAS? Because obviously we don't want to turn the head like backwards. So this is a couple of things that need to be figured out. And then of course, there's the quest state. How far along are we in the various things that we need to do in the game? Are there any like achievement process or progress that's happening right now? So where are we there? So all of these things need to be computed. And RAS is not the only character. So there's a whole bunch of these other so-called non-player characters which evaluate what they should do based on a behavior tree. And for example, if one of the characters decides that he should move over here and sit down and maybe read a report, then we need to figure out how to get there. So we have to do some kind of path planning, maybe using a star to figure out how we can navigate from here to there. Then we have to evaluate, just like for RAS, the kind of movement state depending on what the character is supposed to do. And so again, are we on the ground when we're walking? Are we going up and down the stairs? So we have to figure out where we are. Are we colliding? Then we also have to evaluate the animation state for each one of those characters. And then there's other elements. For example, in Psychonauts 2, we had this fairly sophisticated dialogue system where you can overhear these non-player characters and their conversations. And the idea is that you can kind of learn something about the game world and just make it feel rich and full of actual characters. But this too has to be figured out. Like you can't just launch these dialogue lines for all the characters in the world, because that would just be a cacophony of noise that doesn't make any sense. And then, of course, the other elements there, for example, this computer thing over here that you can use for your upgrades, and some other buttons and things like this, and of course doors. And doors on its own are a really difficult thing because they have actually fairly complicated state tree, right? Like first you need to figure out, is the player actually nearby a door? And then even if that's the case, have we met all the conditions so the door can open? Like is there some kind of quest state maybe until the door opens, or do you need a key? And then if a door has opened, but maybe you're walking away and it should close again, what happens if some other non-player character has now walked into the door frame? And so there's a lot of edge conditions that need to be figured out. And so you can see there's a lot of very different kind of heterogeneous things that need to be figured out in order to advance the game. And because of that, a lot of game engines have a high-level scripting language to represent or to aid this kind of implementation of the game logic. And in Unreal Engine, we can use Blueprint. And so Blueprint is this visual scripting language that you can see here that allows like gameplay programmers and game designers, which often don't have a programming background, to implement these actions that's supposed to happen based on certain events. So for example, here we're starting some kind of movement maneuver, and then we can figure out based on some pin that's equipped whether or not, for example, materials on RAS's model should be changed in some way, or which animation state to launch, and so on. And this can get quite complex. For example, if we look at some parts of, that's not even all of it, of RAS's event graph that defines all the logic just associated with RAS, we can see there's a lot of stuff happening here, a lot of boxes and connections. And in fact, in Psychonauts 2, we had around 6,300 of these script objects, and they totaled around like 27,000 blueprint functions. So you can just see the kind of the sheer amount of complexity that implements the kind of game logic that's in this high-level representation. And I was joking earlier about kind of computing fun as kind of a quantitative value, and that of course doesn't work, but fun definitely exists and is materialized, and it's right here. It's in this implementation of the game logic where the fun essentially exists. And when you start to make a game, you often don't know what will be fun. Is it fun to press a button to open a door, or should you just walk up to it and it opens automatically? And in order to figure out what will be fun, you have to be able to iterate quickly on the logic. And so the game designers and gameplay programmers need a way of very quickly trying out various things to figure out what will make this experience of playing the game fun. And that's why it's important to have this high-level representation that you can very quickly change. And for example, you don't need to wait to compile and so on. But this can get quite gnarly. So here we have the animation state transition graph for Raz's lower body, so just his legs. And you can kind of see, this defines what should happen, for example, if you're bouncing on a trampoline, but then, maybe you are, in the air off the trampoline, and then, can you fall against the wall and slide against the wall? And so this is the kind of state transitions that are defined here. And you can see there's a lot of it. And in fact, figuring out what's going on if something doesn't work the way you think it should, like figuring out and solving bugs, is quite tricky. And I have a lot of respect for the gameplay programmers and animators who have to go in here and then work with this very complicated graph to solve issues. And for me as a low-level programmer, I see that we have a lot of random memory access in these high-level representation because it's not really designed to be optimized for parallel execution. And in fact, let's look at this in a more systematic way, and let's compare how we work with graphics, or specifically how the data is laid out for graphics with gameplay. So for graphics work, we have nice contiguous arrays that are aligned in memory. We have predictable memory access patterns, and the operations that are done on various elements are all the same. So that's why we were saying earlier that we can run the kind of projection on these vertices all at the same time, or compute the color for these pixels all at the same time. There's minimal to no branching in the graphics pipeline. State mutation is often from read-only to write-only output, so that's nice and clean. There are no dependencies between the elements, so that's, like I said earlier, with the vertices and pixels. And because of that, it means the execution order doesn't really matter. And all of this together is a recipe for maximal parallelism. So we can really use all of these parallel shader cores and, working on even getting the frame ready on the render setup step, we can nicely parallelize this. On the other side, for gameplay logic, we have data that's scattered all across the heap, and our memory access patterns are random, and often we have to chase pointers to the heap. So for example, for the example of the door, a character walks up to a door. First, you need to figure out, is it the main character? And then you have to follow, the character pointer to see where the inventory is in memory, and then in the inventory you have to go through all of the items in the inventory to figure out, for example, if this player has the key. So you're just chasing memory through the heap to figure out whether or not the condition is met, so you can actually progress. So that's the random access pattern. Now the operations that are done per element are very different. So what we do and have to calculate for a door is very different from what needs to be computed for an NPC or the main character. There's heavy branching. In fact, I often joke that gameplay is nothing but branching, right? So if you, for example, press a button on a controller, it's very context specific. If you're nearby an enemy, pressing the button might trigger an attack. But if there's no enemy nearby, maybe this will trigger some other, like a dash or a roll. So making these decisions is just essentially layers and layers of if statements. And the state mutation here is read, modify, write on shared memory all over the place. We have very complex dependencies between objects, both on a high level as well as on a kind of low level representation of these buffers. And execution order matters a lot. First, we have to figure out where the player should be based on the player input before we can, check collisions, for example, so evaluate the physics state. And we have to do that before we can actually compute the pose and evaluate the animation state. And we can't just execute this in any random order. But all of this put together, right, is something that makes Gene Amdahl quite sad, because this is very, very difficult to parallelize. So that's the state. It's very difficult to parallelize the gameplay logic, but we do have all this additional computational resources on the CPU. So we have all these like additional cores and threads. We want to do something with that. And that's why a lot of the game engines have this idea of these main threads, like the game thread and render thread, that will then delegate work to worker threads. So for example, we could run the physics simulation in parallel to some other work on the game thread, or evaluate the animation state in parallel to other work on the game thread. We have already seen that we can compute the frustum culling, like the visibility state, in parallel. So we put work on worker threads there, and can use some of the CPU resources that way. And of course, this is a very conceptual model of what this could look like. Let's look at a very specific example. So here I took a CPU trace from a random frame in our game Keeper with the walking lighthouse. Just to show you kind of the amount of parallelism that happens. And the details here really don't matter, but I do want to point out that here we first kind of zoomed in on these main threads. So we have the GPU at the very top doing its thing. And then underneath it, this kind of main block in the middle is the game thread kind of computing the state for the next frame. And you can see, for example, that we have the execution order here. So we have a big chunk of stuff that happens before physics, pre-physics. Then we have something that happens during physics. So meanwhile, while physics is computing collisions, for example, we're doing some other work. And then we have post-physics, where we take the results back from the physics simulation and integrate it with the world. And just visually, you can see just there's a lot of stuff that needs to be computed. Even for a fairly linear game like Keeper, you have a lot of like different objects and states that need to be computed. And then here at the bottom, you have the render thread that's gonna prepare the data for the graphics card that's running in parallel to these. And I do want to point out here that we have this really long block down here, right? And this is where we actually are stalling and waiting for the graphics card to be done with the occlusion culling data. So we're kind of waiting for the graphics card to come back with the data for the occlusion culling that we requested for the previous frame. And this is not ideal. Like this is a bubble. We don't want to wait here. And so we would need to like do some work to reschedule the operations here, so that we don't waste this like nearly 7 milliseconds to wait for the data to come back. But the point is, all of these things kind of run and overlap, like we saw earlier. And then if we zoom out to look at the whole state, what all of the kind of threads are doing, we can see something like this. So again, we have these main threads up here, the GPU, game thread, render thread, and then all the other yellow and purple things is code that's running on other cores. So we would have audio work here, for example, somewhere. We have physics simulation, animation evaluation is going to be one of these yellow blocks, as will be the frustum culling. So you can see there is a lot of parallel execution happening on these CPU cores, but there's also a lot of empty space. So all of this dark gray here means that we don't actually do any useful work on these hardware threads. And so that means the CPU cores are just sitting around idling. And that's not ideal. Like, we would like to fill these spaces with useful work to get most out of the hardware. And but that's kind of tricky to do with these model where we have these main threads. Now that I'm coming kind of closer to the end of my talk, I do want to point out that there are other ways of doing this to get around this specific problem. For example, our sister studio at id Software has been working on Doom for quite a while. And starting with Doom Eternal, they ditched this idea of having these main threads, so like the game thread and the render thread. And instead, they switched over to a job-based architecture. So essentially what this means is that instead of having these long synchronous chunks of time allocated to computing the game state, and then the command buffers for the graphics card. You kind of split up the work into modular units that you can compute independently. And so by doing that, you can define your jobs and the dependencies between those, and then execute those on all the worker threads that you have. So you can, in theory, fill the CPU much more nicely with useful work and pack it more densely like this. And in the case of Doom Eternal, I think Axel said there's around like 100 jobs per frame that needs to be executed. But of course, this means that you have to lay out your data very carefully. You have to essentially design your game entirely around this idea of using a job-based architecture. And so, at the first glance, obviously, this idea of using a job-based architecture looks very appealing and the ideal way of doing it. But it comes with a big drawback, and that is you really have to focus your engineering efforts on making this work. And this is possible if you make a game where you kind of already roughly know what the game will be like. So in case of Doom, you can kind of see that this is what it looked like over the ages. So in the mid-90s, we had Doom 1, then Doom 3 over here. I think this is Doom Eternal, and then finally Doom Dark Ages. And they're all, as a game, very similar. It's a shooter game. You have this gun in front of your face, and you're running after monsters and shoot them. So kind of the overall flow of the game has stayed kind of consistent over the years. And I'm not saying this to criticize Doom. I love the series. I played Doom pretty much since the mid-90s, since Doom 1, and have played all of these games, and I love them. And, the games certainly have become much more sophisticated over the years, just visually, from a sound perspective, also just kind of the gameplay has a lot more nuance these days, and it's a lot of fun. I highly encourage everyone to play it. But if you're making a game like this, where you kind of already roughly know what it will be like, you can then take all of your engineering resources and put it on something like this by making sure like a job-based architecture works. And then you can, get a lot more out of the CPUs and therefore, run the game faster. Now, in contrast to that, for us at Double Fine, we're infamously never make the same game twice. So, for example, here you have Psychonauts 2, we have Keeper with the Walking Lighthouse, and then just recently we released this pottery-based multiplayer game called Kiln. And all of these games are vastly different. And since these games are so different from each other in terms of the feel and the gameplay logic, we need a lot of flexibility when we implement the gameplay logic to figure out what the game will be like and what will be fun. But that means we need the flexibility to iterate quickly on the game logic, and we can't, fix our memory layout at the beginning of the project like you would have to do in order to make a job-based architecture work. So that's one of the reasons why we kind of still using this kind of idea of these main threads, and that's why we, can't get the same utilization of the CPUs that people at tech get for with Doom, for example. So it's kind of like a high-level decision, essentially, when you work on a project, what you want to focus your development resources on. And that's all the time I have today. I hope you learned something new and interesting about how we're using parallel computation in games. All right. Thank you very much.